Let's add another concept from our science of work, the law of large numbers. What this law states, often referred to as the central limit theorem, is that no matter how skewed the variation is of independent samples within a population size, the mean of all samples from the same population will be approximately equal to the mean of the population, given enough sample size. And projects always offer enough tasks and complexity. In simpler terms, the more samples you have, the more distribution looks like the standard bell curve we're all so familiar with. Question is, what does this do to help us with our goal of more throughput, less operating expense, less investment, greater agility, greater reliability, and better quality? Think about a single project and imagine we could plot the demand for a given resource type over time. On some days, demand is very low, and others, it's very high. There's an average we can draw through this. If, however, we were to resource the project to the average level, we'd be unable to meet the peak demands, and we would fall behind on schedule. If, on the other hand, we were to resource up to peak demand for those few occasions when it's required, in most cases we'd go broke paying the holding costs of the resource when they were not doing any value-adding work. Multiply this by the total number of projects in your program or portfolio, and pretty soon you're talking real money. You say, how about if we pool the resources? And that's a very good idea, to be sure. However, whilst necessary for the full solution, it's not sufficient. As we can see, the aggregate demand has far less variability in demand than each individual project on its own. This means that as long as we know which is the priority task on the priority project, she'll be right. But priorities are so often set by the dog with the biggest bark, not necessarily the one with the fiercest bite. If we're going to have a complete solution, we need a valid signal based on criteria of sound reason and logic for the assignment of a given resource to perform the work on a particular task. I'll repeat that because it represents the heart of the problem we're trying to resolve. How we make sure the resources we have are being used to optimum effect for the value creation as a whole. So, if we're going to have a complete solution, we need a valid signal based on criteria of sound reason and logic for the assignment of a given resource to perform the work on a particular task. Let's take a look at how the science of work goes about creating that valid signal. First of all, we need to drill down to the level of a particular task, say going for a 10-kilometer ride. If I was to ask you how long will the ride take, you'd no doubt tell me it depends. What's the terrain like? How heavy is the traffic? How fit am I? Is it a race? And a host of other factors. Let's imagine a plot of the frequency distribution over time. A P10 estimate means that in only 10% of all the times you have been for a 10-kilometer ride, would you have been able to come at a duration of A or less. Likewise, a P50 estimate gives you a 50-50 chance you will have completed the 10 kilometers within the duration shown at B. And a P90 estimate tells you, at C, what duration covers 90% of all times you've clocked for a 10-kilometer cycle. In other words, if you want to be sure with a 90% confidence level that no matter what you can complete the 10 kilometers within a certain amount of time, you would quote the task duration at C. Now comes the genius of Dr. Goldrat's innovation in productivity, the concept of the buffer and buffer management. Exploiting the law of large numbers to tame uncertainty and deliver higher performance with less risk. Let's imagine you can sum up the difference of the durations between the P90 and the P50 estimates. How do we do that, you ask, if we don't really know to any degree of accuracy what a P anything is? Some people fool themselves that they can determine these durations accurately by looking at past performance. But this is a mirage. Past performance contains all the unproductive work habits baked into the figures. And when you're being measured on your ability to conform to a number, are you not more likely to give the maximum estimate you can get away with? No. We need a new way to think about what a P50 is. Fully kitted, that is, all materials, documentation, people, rooms, environments, and anything else needed to complete the task is ready before you start. It's much like the pit crew being ready with everything necessary to perform the pit stop in record time. Work in flow, no multitasking allowed. You're left to engage in the task from beginning to end without interruption so you can attain psychological flow. Maximum collaboration. Everyone is clear about what the constraint is and work together to ensure the flow of value doesn't get bottlenecked. Now what happens when we put a 100-day schedule together made up of 5 tasks, each of which is 20 days? Well, let's say for argument's sake that the P50 estimate is 10 days for each task. By the law of large numbers, all of my wildly varied distribution curves, when aggregated, take on the shape of the famous bell curve of the normal distribution. And because a normal distribution is evenly split down the middle, we can make a good enough rule of thumb that the proper sizing of the buffer is equal to half the duration of the chain feeding into it. Thus, my 100-day project becomes a 70-day project, in theory. But as a client once said to me, theory is the dinner jacket you take off when your car gets a puncture. What happens in practice? Let's take a look at this somewhat more complex scenario. I have 2 work streams running in parallel. Based on tracing the longest chain of dependent events, known as the critical path, we get to a total duration of 84 days. Note in workstream 2 that task 3 can start early or late. We'll come back to this in a short while, but first let's see what happens when we add resources to this model. In this scenario, we've shown task 1 and task 4 as both requiring blue resource A. This blue resource cannot be in 2 places at once. One way or another, we have to resolve the resource contention, either by adding additional blue resources or by stretching out the due date. If, in this example, we resolve the contention by allowing task 4 to start only once task 1 is completed, we've caused our project duration to extend from 84 to 100 days. In addition, we've added more slack into the schedule, meaning both tasks 2 and task 3 have a choice of starting early or late. The usual inclination is to start early, as it gives the hope that risk will be mitigated. However, there's significant risk associated with flooding the engine with work in process. How many open work fronts can you effectively manage? But if everything starts as late as possible, then everything is on the critical path, and a delay anywhere is a delay to the whole project. How do we get back on track to our goal of delivering more throughput at low cost with greater speed, reliability, and quantity? Well, we use our science of work. We reduce our tasks down to their P50 duration. We include a project buffer, which is half as long as the critical chain feeding it. And this makes the overall project duration 75 days, a 25% improvement on the normally calculated resource-leveled critical path. And we start our feeding tasks, that is tasks 2 and task 3, as late as possible. But we make sure that at each integration point with the critical chain, there's a buffer, a feeding buffer, acting as a shock absorber for any risks to late completion of those chains of work.